All right, everybody. Last time when we were here, we talked about empirical formulas and mass percent composition. We're going to pick up right there where we left off with it when it comes to empirical formulas, because not only do we want to be able to identify an empirical formula or determine an empirical formula based on a molecular formula, given some data, we want to be able to calculate an empirical formula. And so this is another reason why we spend some time talking about empirical formulas, is because you can calculate it. And so let's go ahead and get into that. As I mentioned last time, mass percent composition really is just a formula, and it doesn't fit very well with the problem-solving system that we used before. And the same thing is true, I think I warned you before, the same thing is true when it comes to calculating empirical formulas. It doesn't really fit well with our 1, 2, 3 problem-solving method. So we're going to have to deal with calculating empirical formulas in a slightly different way. So I'll show you a method to do that one that'll be a little different than it was before, but it'll still help you organize your problem solving so that you can think about it a little bit more straightforward. Let's see. There's something I want to say about empirical formulas. Let's go back to something like H2CO. We said that that was the same empirical formula for glucose, C6H12O6. The empirical formula for glucose is CH2O. And I want to rearrange this here to CH2O. Now, glucose and formaldehyde are different molecules, but their empirical formula is the same. They have the same ratio of atoms, and the ratio of atoms is 1 carbon to 2 hydrogens to 1 oxygen. And the same is true with glucose. And so we define the empirical formula as the lowest whole number ratio of atoms. In other words, 6 carbons, 12 hydrogens, 6 oxygens is a ratio of atoms. It is a whole number ratio of atoms, but it's not the lowest whole number ratio of atoms. And so the empirical formula is specifically the lowest whole number ratio of atoms. Okay, but I want to kind of get at something else as well. And this one is going to take a little bit of a leap of understanding. Remember that a mole, 1 mole, does mean a particular number of atoms. So 1 mole of atoms is equal to 6.022 times 10 to the 23rd atoms. So remember that I'm counting atoms, or I'm counting molecules. I'm counting things when I talk about moles. So I want to tie that into empirical formulas in the following way. If an empirical formula is the lowest whole number ratio of atoms, then it's also the lowest whole number ratio of moles of atoms. So I already had this definition. Empirical formulas are the lowest whole number ratio of atoms. I already had that part. But I want to add the next part, because remember, if I'm talking about moles, I am talking about counting atoms. So I'm going to insert the definition for moles here. An empirical formula is also the lowest whole number ratio of moles of atoms. And so let's just take that to the given an example real quick using glucose. For glucose, I have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms for every 1 molecule. So I can say we did this before, 6 atoms of carbon for 1 molecule of glucose. But remember when we said we could actually do the relationship several different ways? I didn't specifically spell it out, but we also did the relationship this way. 6 moles of carbon for every 1 mole of C6H12 of glucose. We could even do it this way. We don't do this in chemistry, though. We could say 6 dozen carbon atoms for every 1 dozen glucose molecules. We could say that. We don't do that in chemistry, but we could, right? The ratio is the same. Adding the word that means a particular number doesn't change the meaning of the ratio. And so when it comes to the empirical formula, CH2O, there's 1 carbon atom for every 1 empirical formula of CH2O. And so we can say there's 1 mole of carbon for every 1 empirical formula mole of the molecule. We're going to take advantage of this fact to solve problems about empirical formulas. So let me actually get into some examples of that. Let's say a sample of a compound contained 24.5, make that a little neater, 24.5 grams of nitrogen and 70.0 grams of oxygen. Calculate the empirical formula. All right. So we want to calculate the empirical formula of the molecule. That means we want to figure out what X and Y are. The one thing we know about X and Y is that they're whole numbers. One thing we know about X and Y is that they're whole numbers, and we're going to work towards that. And so here's how we approach it. I'm just going to kind of give you an idea of how we would do this problem solving. It's a little different than before, but I do organize my thoughts in a table. You can do it any way you want, but I tend to organize my thoughts in a table. I do atom, mass, in grams. I do the number of moles. And then I do a mole ratio. Remember, the mole ratio is the same thing as the lowest whole number ratio. They're equivalent. We already showed you how if in glucose there's there's 1 carbon atom per 2 hydrogen atoms. When I'm talking about its empirical formula, the same is true for moles. There's 1 mole of carbon atoms for every 2 moles of hydrogen atoms in the empirical formula for glucose. So the mole ratio will actually help us figure out what this empirical formula is. Now, I put down mole ratio number 1 and mole ratio number 2 because I might need to deal with them again. I might need to change the mole ratio, and you'll see. The first time you calculate a mole ratio, you might not get only whole numbers. So you might have to do some other math tricks. And so this step isn't always needed, but if it is needed, it's math tricks. It's math tricks. All right, so let's write it down. I've got nitrogen and oxygen. Those are the two things that I have. And the masses are given. It's 24.5 grams of nitrogen and 70.0 grams of oxygen. Okay, well, how do I figure out how many moles there are? Well, I already know how to do this calculation. 24.5 grams of nitrogen. And I look at the periodic table and I say that nitrogen is 14.01 grams per mole. And using this quick calculation, I can calculate the number of moles in 24.5 grams. So I get 1.749 moles. Same thing with oxygen, 70 divided by 16. And I'll go ahead and write it down this time. I get 1.749 mole of nitrogen. And then for oxygen, it's 70.0 grams of oxygen divided by 16.00 grams oxygen per 1 mole. And I get 4.375 mole of oxygen. 4.375. Okay. And so I usually stop here and I say, look, nitrogen 1.749, oxygen 4.375. I do this because I want to say, is this the right answer? And I pause and we talk about it usually in the classroom and we go back and forth a little bit, but we come to the conclusion that, well, it's not the right answer for X and Y. It's not the empirical formula because the empirical formula is the lowest whole number ratio of atoms. Is this a ratio of the atoms contained in this molecule that has nitrogen and oxygen, and is it a molar ratio? The answer is yes, it is the ratio of atoms, but it's not a whole number ratio. And so what we have to do is we have to take this non-whole number ratio and we have to turn it into a whole number ratio. And this is where we do some work here. This is how it's done. And so what we do is we take the lowest value, we take the lowest value of moles and divide all mole values by it. So let's take a look. Which number is smaller? 1.749 or 4.375? Which number is small? Right, the number for nitrogen is smaller. So we take the lowest value of moles and we divide every number by it. So I'll do the hard one. 1.749 divided by 1.749, that's 1. There's the hard one. Now here's the easy one. I'm sorry, am I saying that backwards? It's not the, wait, okay, anyway. 4.375 divided by 1.749, and I get 2.5. Okay. Well, now I've got nitrogen. And so what I want to do is I want to just rewrite this. Nitrogen 1.749, oxygen 4.375. And now I've got nitrogen 1, oxygen 2.5. So what do I need to do now is I need to take this and I still need to get it into a whole number ratio. I'm going to need to use some math tricks, as I mentioned before, in order to do that. So how do I do this? So what I do is I have to, exactly, you guys are starting to figure this out. I have to multiply. I have to multiply here. I have to multiply both values by a number that still yields a whole number. And it has to be the lowest whole number. And how I do that is I look at this decimal. I look at the decimal. I'm going to look at this decimal value, and I'm going to think about it in terms of a fraction. 0.5 is equal to the fraction 1/2. And I know that if I multiply the fraction 1/2 by 2, I get 1. So in other words, if I have a fraction that's 1/2 and I multiply it by 2 by the denominator, then I get a whole number back. And so I'm going to multiply by this fraction both numbers, and then I'll get whole numbers back. So 2.5, and so the fraction is 1/2. Since the fraction is 1/2, I want to multiply every number by 2. And so 1 times 2 is 2. That was pausing for dramatic effect there. 2.5 divided by 2 is 5. And so now that I've gotten here, I've got whole numbers, check. And it's the lowest ratio of whole numbers. I'm done. I've figured out the empirical formula, N2O5. Okay, this is essentially what you have to do. There's not anything else to it. The biggest challenge for students happens here in this step. This is the biggest challenge for folks, is right here. Because it's easy to sort out that 0.5 is 1/2 and we multiply that by 2. But what about that? What do we multiply that by? And so it gets to be a little bit of a challenge. Okay. So let's actually go through those. Let's take a look at what before we do any other practice problems, let's define some of those common decimals that mean fraction. The question is, are we always going to be given the mass, or will we have to get it? You'll always be given the information you need. So I don't want to say that you'll always get the masses, but you'll always get enough information to determine the masses. So there might be another extra step of difficulty, and I'll show you an example of that here in just a second. All right. Okay, common decimals that equal fractions. We already talked about this one, right? What's this one? Okay. What are some other common ones? What's 0.25? That's 1/4. What is 0.333? You know that one? This one's 1/3. You've got 0.666. What was that one? 2/3. And 0.75. That's 3/4. Now, here are the common ones, but there's also, just real quick, these are the halves, the thirds, and the quarters. There's also some eighths. 0.125, that's 1/8. 0.325, that's 3/8. 0.625, that's 5/8. And 0.875, that's 7/8. These by far are only show up in the most advanced difficult problems. But I did want to at least have them written down for you so that you could see these decimals and the values that they hold as far as their terms and fractions. They're fractions of 8. So how do you deal with these fractions? What do you do when you find these decimals? We're going to multiply here by 4. We're going to multiply by 3. We're always multiplying by the denominator. Multiply by 2. Multiply by 3. Multiply by 4. And that gets us whole numbers when we do that multiplication. This one would all be multiply by 8. But again, you won't really see a lot of those, if any at all. Okay. So I'll say it now, and I might chant it later on as well. But remember, we multiply, we don't round. We don't round. We multiply and not round. Students often mess this part up. So the question is this: there's never going to be a weird decimal that's not on that list, because then there would be no whole number ratio, right? The answer to that question is yes, essentially, never. But we might get a weird decimal, and in advanced problems, you might have mole ratio 1, and then you multiply to get mole ratio number 2, and you might have to do it again, mole number ratio, this is very rare, number 3, and there might be a weird set of decimals here that you have to multiply in order to get to here. So maybe you get 0.25 and something different, but you're right, there really won't be one. So let me just backpedal a little bit now that I'm thinking about it. No, there's not going to be a weird decimal. Here's the one situation that students get confused about. You might end up with something like this, or even something like this, because you can introduce quite a bit of rounding errors in this particular situation. What do I call these numbers if I see this in the mole ratio after I've done a calculation? Am I stuck? Did I mess up here? Yeah, really, I'm just going to call this one 5, and even this one I'll call 5. I might even get 5.02. I'm still just going to call that 5. So within a couple of 1, 2, or 3 100ths, you're probably okay. You're probably right. You just introduce some rounding errors. And so there really is a large degree of number sense involved in this particular problem. The same thing would be true if you get something like this, 2.239. Well, maybe you did some rounding errors, or you're using a periodic table with very few significant figures. I would probably go ahead and try to call this 2.25. But hopefully you wouldn't get something like 239. I wouldn't be surprised if you saw something like this, 2.247. That's 2.25, right? So this does involve some number sense. Now, the examples in the book, they're not going to involve any sort of weirdness like this. Most of the examples that you come across on the internet probably won't involve anything like this, but just be prepared to use your number sense to decide, is it time for me to multiply, or did I actually come up with a whole number and I just need to write that whole number down? And so there is going to be a little bit of a number sense challenge in that regard. So let's do a few more examples and let's see how these problems might manifest themselves. Okay, here's another way. Let's do so a compound with 3.24 grams of titanium is found to have 5.4 grams of oxygen. What is the empirical formula? Okay, so it's titanium. So atom, mass, mole, that's number of moles, and then mole ratio. Maybe we'll need another mole ratio. Let's see. Titanium and oxygen. The mass is given here, 3.24 grams and 4.50 grams. Now, this is the last time when I'm doing an example that I'm going to write down the actual conversion from grams to moles. At this point, I know every single one of you has done all of the practice you need to do these one-step conversion problems. And so I'm going to do it one more time. Titanium is 47.88 grams for 1 mole of titanium. But from now on, after this, I'm just going to go from here to there without writing down the problem. You should just be taking this mass, finding the molar mass on the periodic table, and dividing. So you should be getting close enough to having the confidence to not have to write that down in order to do that. Robin, I'm going to take your word for it. So that's 0.067. Any more sig figs there that we're dropping off? So 0.6767 because there's a 9 after that. Thank you. You're right. Look at the problem. The problem says 4.50 grams here. So let's do that one. So this one was 0.06767. And the oxygen is 4.50 grams of oxygen, 16.00 grams per 1 mole. So 4.5 divided by 16, I get 0.2813. I'm going to 0.2813. 0.2813. Okay, what's the lowest whole number ratio? What's the mole ratio here? What's the smallest value? 0.2813 or 0.06767? Well, the first one is the lowest value, so I'm going to do the really hard part for you. 0.06767 divided by 0.06767. There you go, 1. Yeah, so this is an important point, I think, that is brought up, and I think it's definitely worthy of talking about. With these types of problems, you don't want to do any rounding. And the reason you don't want to do any rounding is that you need as many digits as possible to avoid rounding errors. So I'm not going to, even though the mass is given in 3 significant figures, I'm going to go ahead and write down 4 or 5 significant figures for the number of moles, so that when I do the division, I'm going to have the least amount of rounding errors, so that when I look at the mole ratio, I'll be able to see more clearly what if I get into the situation where there's decimals and I need to figure out what fraction it is, I'll see more clearly what fraction it is. No, oxygen isn't the lowest value of moles because 0.06767 is smaller than 0.2813. And so I want to divide everything by the smallest number. So 0.2813 divided by 0.06767. What do I get? 0.2813 divided by 0.06767. Huh. Oh, geez. Okay. So I made a mistake because I'm getting a problem and I'm reading it, and it's about 1.5 feet away from me, and so I'm old, and so I have bad vision, and so I didn't see the value of grams of oxygen correctly. My bad. And how did I know that? Look at the value that we get. We calculate 4.156938. Well, that's not any of those common fractions. And just like Diana pointed out earlier, if you get a value that's not one of those common fractions, that's a hard stop. And you have to go, what's going wrong here? What happened? And so in the book, I just didn't see it. And so let me erase this. 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 Let's go back and put the right value there. Let me lean a little closer. It's 2.16. 2.16. So 2.16 grams of oxygen divided by 16.00 grams of oxygen, or 1 mole. I get 0.135, 0.135. And now let's take that and divide it by 0.06767. Aha! There, that's better, right? What is 1.995? The formula is Ti1O2. And so 1.995, this is where you need your number sense, is 2. 1.995 is 2. All right, let's try another example. I'm going to do a bunch of these here. So see if I'm going to lean really close so that I can see it correctly. The mass percent composition of a compound with only carbon, hydrogen, and oxygen is carbon, oxygen, hydrogen. 60.00%. 4.48%. 35.53%. Okay, calculate the empirical formula. Atom, mass, moles, mole ratio 1, and maybe mole ratio 2. So the comment was made, that doesn't add up to 100%, Eric. 60 plus 35.53 plus 4.48 equals 100.01. Is that 100? Boys and girls, is 100.01 100? Yes, it is. Yes, it is. Gotta have that number sense. Gotta have that number sense. Yep, close enough. Right? Within a couple of 100ths. You're good. So what are my atoms? Carbon, hydrogen, and oxygen. Okay, what are the masses? What are the masses? Uh-oh. 60 million. 60? What? Why 60 for carbon? 100, these are percentages. Aha. I love this. So this is great. This is good times. So the comment was made, 100 grams, 100 grams, 100 grams. Well, I'm not giving you the masses in this case. I'm giving you the mass percent composition. So what does that mean? That means that in any sample, I don't care if it's 0.5328 grams or 5,938 grams, 60% of the mass of the sample will be carbon. 35.53% of the mass will be oxygen, and 4.48% of the mass will be hydrogen. So it doesn't matter what the mass of the sample is. Okay, so, well, what if the mass was 100 grams? If the mass was 100 grams of the sample, then what would be the mass of the carbon in 100 grams? What's 60% of 100 grams? Right, 60 grams, 35.53 grams. Oops, I did that backwards. 4.48 grams, 35.53 grams. So you just use the mass percent compositions as the masses, Because you can always say to yourself, well, what if I had a sample that was 100 grams? And this is the first example in chemistry, in all of chemistry, where in order to solve a problem, you have to make an assumption. You have to say something to like the following. You have to say, well, I'm given some data, but the data that I'm given isn't what I use to solve the problem. But with the data that I'm given, if I hypothesize a sample, if I devise a hypothetical sample, then I can use the data to get the information that I would use in order to solve the problem. So yeah, I mean, the short of it is you can assume that it's 100 grams. You could say, what if the sample is 100 grams? And the reason why we say 100 is because it's easy, right? If I have percentages and I assume that the sample was 100 grams, then I don't really have to do any calculations to figure out what the individual masses are. If I assumed that the sample was 4,325.5 grams, could I do the calculation? Absolutely. I would just have to figure out what 60% of 4,325 point, whatever I said to, whatever that is, I have to figure that out. When you assume 100, you don't really have to do any math because what's 60% of 100? 60. What's 35.53% of 100? 35.53. What's 4.48% of 100? 4.48. Right. We just use 100 because that makes the math easy, makes it something we can do in our head. So now that we've got the masses, we're going to do everything else the same. So carbon is 60.0 grams divided by 12.01. I get 4.996. Hydrogen, 4.48 divided by 1.008. I get 4.444. And 35.53 divided by oxygen, which is 16. I get 2.221. And so I just want to pick the smallest number. The smallest number is 2.221. And I want to divide every value by that one. So I'll do the hard one. 2.221 divided by 2.221 is 1. I don't ever get tired of that joke. So hopefully you're doing the other division on your own while I'm making that joke. That's the point of it. But then 4.996 divided by 2.221, I get 2.249. And 4.444 divided by 2.221, I get 2.001. Right. What am I left with here? What do I do with this set of values? Remember, I round and I don't multiply. And so many students would have the mistake of doing this. They would say, all right, I'm done. The formula is C2H2O1. And they would round 2.249 down to 2. And that's not what you do. You don't round, you multiply. So you have to identify a common fraction here. Can you identify what the common fraction is? Can you identify what the common fraction is? It's here. It's right here. What's the common fraction? Right, it's 1/4. 2.249 is essentially 2.25, and 0.25 is 1/4. And so I need to multiply everything. I multiply everything by 4 times 4 times 4 times 4. So I get 2.25 times 4. What do you get? You get 9. 2 times 4, 8. 1 times 4, 4, I think. All right, so what's the empirical formula? C9 H8 O4. Okay. So far, so good. So far, so good. Let's do a couple of more examples. Let me show you how I can really mess you up here. Let me show you how I can really confuse you. Okay. Okay, here's an example. A 1.60 gram sample of a compound containing only nitrogen and hydrogen is found to have 1.4 grams of nitrogen. That's a period. What is the empirical formula? Okay, so my atom is nitrogen and hydrogen. Mass, mole ratio. Maybe I'll need another mole ratio. We'll see here in a second. Well, you're going to have to deal with some confusion here. What do I do? Mass of nitrogen, given 1.40 grams. Oh, it's not so confusing there, is it now, Mr. Jared? $98.6. No, nope. Careful about the problem, right? What is the, this is where I really do need you to dig into the word problem and sort out what is missing. What do I give you? What do I tell you? I tell you that the sample itself, the total mass of the sample is 1.6 grams, exactly. And I tell you what the mass of the nitrogen is. And so you have to subtract the mass of the nitrogen from the total mass of the sample, because telling you that it only has nitrogen and hydrogen means when you do that subtraction, the only thing that you're left with is the mass of the hydrogen. So you do have to do a subtraction, but it's not from 100. You have to do it from the mass of the sample. So the mass of the sample was 1.60 grams. And so subtracting them 1.4 from 1.6, I get 0.2. And so now I've got all the information I need to solve the problem. So 1.40 divided by 14.01 is the mass of nitrogen. I get 0.09929. Same thing for hydrogen, 0.2 divided by 1.008. I get 0.1984. So let's take the smallest value, which is the first one, and divide it by itself. I'll get 1. But then 0.1984 divided by 0.09929, I get 1.998. Am I done? Yeah, my bad here. This is a 0.9993. 0.1984 divided by 0.09993 is 1.985. Am I done? I'm still done, right? I'm still done. So 1.985 is still 2. It's still 2. So the formula, or the empirical formula, is NH2. Yeah, so this is where the number sense comes in. If I want to, I can continue, I can round this a little bit. If I round it to 3 sig figs, it might be I'll see it better. 1.99. So what defines close enough? That's a good question. I'd say 1.03 on the high end and 0.97 on the low end. That's probably the largest range that you would see for something to equal 1. Okay. All right, one more. Let's do another example. A compound is found to have carbon, hydrogen, and oxygen. And the mass percent carbon equals 79.37%, and the mass percent of oxygen equals 11.75%. What is the empirical formula? Okay. Carbon, oxygen, hydrogen. Mass, mole ratio. Maybe I'll need another one. Yeah. Well, we can make an assumption that we have a 100-gram sample, and if we do, it's 79.37 grams carbon and 11.75 grams oxygen. What's the mass of the hydrogen? What's the mass of the hydrogen? I didn't give it to you. I didn't tell you the mass percent composition of hydrogen, but this is an example of just, yeah, it's the remaining bit. I'm just leaving out one little piece, and you should be able to figure out the other piece by subtraction. So 100 minus 79.37 minus 11.75 is what's remaining, 8.88 grams of hydrogen. And so that's how you sort out the last little bit if I give you mass percent compositions. Everything has to add up to 100. So 79.37 divided by 12.01, I get 6.609. 11.75 divided by 16, I get 0.7344. And 8.88 divided by 1.008, I get 8.8095. I'm going to carry along an extra digit here. 8.8095. Okay, what's the smallest value? The smallest value should easily be seen to be the number less than 1. So let's divide every number by it. So I'll start off with 8.8095 divided by 0.7344. I get 11.996. 6.609 divided by 0.7344. I get 8.9992. Am I done? Yeah, I think I'm done as well. Carbon is 9. Hydrogen is 12. And oxygen is 1. Yeah. Okay. All right. The last thing that I need to do is talk about molecular formulas from empirical formulas. So we're going to do the same problem, except the problem is going to say, what is the molecular formula? But it's going to have a little bit of information. It's going to have an extra piece of information to help you sort that out. So let me give you an example of where it comes from, though. Let's take glucose again as our example, since we've spent a lot of time doing glucose. What was the molar mass of glucose? You guys remember what that is? I get 180.16 grams per mole. Yeah. What's the empirical formula? So this is the molecular formula. What's the empirical formula? CH2O. Well, I can calculate a molar mass of the empirical formula. What's that? Yeah, it's 1 to 2 to 1. So what's the molar mass of the empirical formula? 12.01 plus 16. What do you get? I get 30.031 grams per mole. Is that right? I think so. Okay, let's go from here. What did I divide by to go from here to here? What did I divide by? Yeah, I divided by 6. 6 divided by 6 is 1. 12 divided by 6 is 2. 6 divided by 6 is 1. What did I divide by here? Well, let's figure it out. Let's figure out what I divided by. Let's take 180.16 and divide it by 30.031. I got 5.999. What do we see? It's the same value, right? It's the same value. 5.999. Everybody at this point should have a little bit of experience and just say, that's 6. It's 6. So if I wanted to go the other way, what if I didn't give you, what if you did a whole problem and the only thing that you didn't have was this? The problem said, what is the molecular formula? And you knew that it was C H oxygen. So you said XYZ. I gave you this value. So all you have to do is go in reverse, right? It's this. And it's not divide by. What did you have to multiply by? Well, what do I have to multiply 30.031 by to get the given molar mass? Well, I have to multiply it by 6. Well, then what should I, if I had to multiply that by 6, then I have to multiply the empirical formula by 6 in order to get the molecular formula, C6H12O6. And so that's all that's the only extra bit that we're adding to this. We're going to take the same empirical formula question and we're going to add the question, what's the molecular formula? And I'm going to give you the molar mass of the molecular formula. So I'm going to give you an extra piece of information that allows you to do that. So let's do one example like that. Okay, mass percent composition of a molecule with a molar mass of 162.26 grams per mole is C. Hydrogen. (8.70%). Nitrogen, 17.27%. What is the molecular formula? All right, so what we need to do is figure out the value of the multiplication value. And so in order to do that, we need to get the empirical formula so that we can divide the molar mass of the empirical formula into the molar mass of the compound so that we can get the multiplication factor. Once we get the multiplication factor, then we can multiply the empirical formula in order to calculate the molecular formula. But everything else is processed exactly the same way. Carbon, hydrogen, nitrogen. So what are the masses? The mass is 74.03 grams. What is the moles? What's the mole ratio? I'm going to make a little bit more room here. Mole ratio. So 74.03 here. You know what? I'm a little bit bored with black. Let's change colors. 74.03 grams. 88.70 grams. 17.27 grams. Okay, moles. So let's calculate the number of moles. 74.03 divided by 12.01. That gets us the moles of carbon. 6.164. Hydrogen, 8.70 divided by 1.008. I get 8.631. And 17.27 divided by 14.01 equals 1.233. Okay, what are the mole ratios? So the smallest value here is 1.233, so divide every number by that one. 6.164 divided by 1.233, I get 4.999. 8.631 divided by 1.233, and I get 7. So I figured out the empirical formula. The empirical formula is C5, H7, O. Sorry, not O, N. So then let's figure out the molar mass of this empirical formula. What's the molar mass of the empirical formula? So 12.01 times 5 plus 1.008 times 7 plus 14.01. I got 81.116 grams per mole. Do pink. Okay, fine. So now I have to sort it out. I was given that the molar mass is I forgot how to do it even. Oh, I have to do it over here. There. I was given that the molar mass is 162.26 grams per mole. I want to divide that by 81.116 grams per mole to get the multiplication factor. 162.26 divided by 81.116, and I get 2.000, and it's not until here that I get any sort of numbers. So the multiplication factor is 2. So I multiply by 2 to get the molar mass. I don't like that pink. I want this pink. So 5 times 2, 10. 7 times 2, 14. 1 times 2 is 2. So the molecular formula is C10, H14, N2. That's it. That's all there is to it. We just add a little bit extra, and you have to just calculate this multiplication factor. So you're taking all of the same information, and then you're just doing a division at the end. You're doing a division at the end in order to calculate the multiplication factor. And then once you have the multiplication factor, you multiply the empirical formula by it. How did I get 81.16 again? I took the empirical formula and I calculated the molar mass of it. So 5 times the molar mass of carbon, plus 7 times the molar mass of hydrogen, plus 1 times the molar mass of nitrogen. So I'm looking that up from the periodic table. 5 times 12.001 plus 7 times 1.008 plus 14.01, and I get 81.116. Does that answer the question? Cool. That's not you. Yep, there we go. That's the one I'm looking for. All right, cool. Okay, that's it. That's that 6th section. That's all of it. That's that whole chapter. And so I'll leave it there for now. We still have some time left today, so it's not, I agree. The comment was made, that's not really so hard. It really isn't hard if you're already good with doing some conversions, even some one-step conversions. If you got a good handle on calculating molar masses and converting grams to moles, then this really isn't a big leap forward. You just have to learn a couple of definitions. And so with that being said, I would agree. But if you don't have that practice and you're not ready to go with converting grams to moles and calculating molar masses, then it's going to be a lot more of a challenge for you. It's going to be a lot more of a challenge for you. So that leaves us out. We're done with that 6th chapter. And so what I want to do now is move along into the 7th chapter. Okay, in that 7th chapter, involves chemical reactions. All right. And so I want to just warn you guys, we're getting into it, right? So if I were to take a graph, let's use this color to make the axis. But then let's use Jared's suggesting we'll use pink. And if I were to say chapter 1, chapter 2, chapter 3, chapter 4, chapter 5, chapter 6, chapter 7, chapter 8, chapter 9, chapter 10, etc. If I were to say, kind of like, what's the challenge? Maybe this is how hard you think it is. Maybe this is how much you have to study. I don't know, whatever you want to say about the challenge. But it goes kind of like this, right? 1 is pretty easy. 2 is pretty easy. There's a little bit of a challenge with 3 and 4. Nomenclature kind of spikes up. It's a little bit hard. Six isn't so bad. Then what happens when we get to 7? This is what's going to happen here. Okay. So far, we've been operating in this sort of zone. You're going to take a quiz over nomenclature, and you're going to get a little bit of a challenge. It's on the graph. So it's on the graph. But as soon as we get out of 6, though, things start to get pretty difficult. And as we progress into chapter 7 towards chapter 8, we're all the way up here once we start chapter 8. And then then chapter 8 and chapter 9 are much more difficult as far as concepts and calculations and all of this. So you can compare, you could say, look, the shaded area is how much time you have to study, right? You didn't have to study much. Didn't have to study much down here. There's a little spike in what you have to study in order to get nomenclature, right? But once you get over here, and we're doing stoichiometry and balanced chemical equations and net ionic equations and percent yield and limiting reagents, you got a lot more work to do. You got a lot more work to do. So I did want to give you that illustration because some students have said to me, well, it's, I don't have time, or I got work, I got family, I got kids, I got dogs and cats, and they take up my time. And so I've got a low B or a C, and I just don't have any time to study. And I'm like, well, you think it's bad now. If you don't find time to study at this point, it's going to get a lot more difficult. And so I expect to see a lot more of you guys in office hours and on Zoom asking questions about the material. Okay, let's get into it. So the first part of this section involves identifying when chemical reactions take place. And so this is kind of a review for those folks that are in 108. Maybe it's, if you're not in 108 yet, though, it's not a review, but what are some things that are evidence that a chemical reaction took place? Let's do this real quick. Is this a chemical reaction? Is this a chemical reaction? No, this is a state change. This is a state change. That's a physical process. So that's not a chemical process. In a chemical process, the formulas of things change. So if I take water and I split it into hydrogen and oxygen, then yes, that's a chemical reaction. So what I want to do is I just want to list some things that are evidence of a chemical reaction. And you need to really put this in your brain just so that if I test you on this, you can reiterate these different things that are evidence of a chemical reaction. Okay, what are the things that are evidence of a chemical reaction? And this really is Chem 107. This is a great example of, we're going to lie to you in the lower level chemistry, and then we're going to tell you the truth in a higher level chemistry, and then maybe that's a lie too. All right, so a color change. Formation of a solid. Formation of a gas. Emission of light. Okay. Heat transfer. Heat transfer. So what does that mean? Getting colder or hotter. That's what that means. Okay. So we're just going to ask you some questions like the following. True or false? Ice melting on a sidewalk on a hot summer day is a chemical change. True or false? Yeah. I see a few folks getting out there. No, right? Yep. You leave an iron nail outside at a construction project and come back 3 weeks later to find that it is rusted. Yeah. That's the kind of questions we're going to ask you, right? It's true in that case. That would be the formation of a solid or color change. Either one of those two things. All right, cool. All right, well, let's get into the next bit. All right. What I want to talk about now is a chemical reaction. And what I'm going to do first is I'm going to diagram it. I'm going to use hypothetical reactants and products. So the question was, hold on a sec. So the question, so before I get any further down this road, the question is asked, can you explain a little bit more about the formation of a solid? Because it could be confusing with a state change. What I really mean about the formation of a solid has to do with mixing two things together. If I mix solution A and solution B together and a solid forms, this is what I mean by this. So if you were to go back to the notes and think about formation of a solid, I mean the formation of a precipitate. Yep. And so the same is true with gases, right? So you guys, what you should know is that if I form a solid from a liquid, if I make ice from water, that's not a chemical change. If I make steam with water, that's not a chemical change. But if I mix Alka-Seltzer and water and a gas comes out, that is a chemical change. If I put two colorless and clear solutions together and out comes a yellow solid, that is a chemical change. So I don't want you to get confused in this idea of forming a solid or forming a gas. That definitely precludes anything that's a state change, right? Baking soda and vinegar, that's going to form a bunch of bubbles. And so that's a chemical change. That's the formation of a gas. And so that's what I mean by that. Does that help? Okay. Okay, so let's go ahead and get rid of that. Let's go back to this diagram. All right, so these are reactants. These are products. And these are the states. What can the states be? Solid, liquid, gas. There's one more state that you'll see. What does AQ mean? That means aqueous. Yep, that means dissolved in water. All right, so let's actually get a little bit more detailed. Let's get a little bit more detailed. So we have the same considerations. What are A and B? What are they? What are they? Reactants. Yeah, these are reactants. In the same way as before, C and D are products. Before, the same thing, X is the state. But what is A, little b, little c, and little d? What are these? These are something different. These are Did I spell coefficients right? I think I did. Coefficients. Yes, cool. They are stoichiometric coefficients. One reason why I always remember how to spell this word is it's one of the, close enough. Did I spell it wrong? Ah, shit. Oops. Yeah. Wait a minute. Yeah. Stoichio. Yeah. Stoichiometric. Yeah. When I was just about to get excited and say one of the reasons why I love the word stoichiometric is it's one of the only English words that has an OI and an IO in it. Very few English words that do that. At any rate, I do like to embarrass myself on YouTube, and so I was able to do that in this video. Congratulations, Eric. The stoichiometric coefficients A, B, C, and D, little a, little b, little c, little d, are what makes the reaction conform to physical reality. Can I say the following? Can I say H2 plus O2 produces water? Can I say that? I mean, is that okay to talk about this in conversation? Absolutely, right? I can say water is formed by hydrogen and oxygen combining. However, I can't use this to do any calculations because the reaction is not yet based in physical reality. Physical reality means that I can't create or destroy matter in terms of chemistry. So that means that if I start off with 2 hydrogen atoms and 2 oxygen atoms, then I really must end up with 2 hydrogen atoms and 2 oxygen atoms. And right now, that's not what the reaction says. Right now, it says that I got 2 hydrogen atoms, 2 oxygen atoms, and I end up with 2 hydrogen atoms and only 1 oxygen atom. So I have to do something in order to make sure that what atoms I put in are the same as the atoms that I get out. And it's just been said in chat, what I'm trying to say is that you must balance the atoms in the reactants with the atoms in the products and vice versa. You have to balance them. And so I could do this. I could say, well, if I have, no, you can't do that. You can't just do this, right? Because that's a different reaction. This would be balanced, but this describes a different physical process. So let's say it in English. Let's say it out. Let's use this reaction as a story. Hydrogen molecule plus oxygen molecule makes water molecule. Not yet based in physical reality, not yet balanced. Doing this does make it balanced, but it changes the story. Hydrogen molecule plus oxygen molecule forms water molecule and an oxygen atom. Do you see how the story changed in the products? The products are different. So if I want this story to be based in physical reality, I have to balance the atoms out. And so what we would say is 2 hydrogen molecules with 1 oxygen molecule produces 2 water molecules. That's the way that we would say that. 4 hydrogen atoms, 2 oxygen atoms is balanced with 4 hydrogen atoms and 2 oxygen atoms. We'll add the states back in later. do another example. Let's start off with a word problem. Let's see if we can convert the words to symbols. Hydrogen and nitrogen form ammonia. Here's the sentence, the story in words. Now let's convert it to symbols. It's going to involve an arrow, right? Because this arrow means form or change or converts or reactants, goes to products. There's a lot of different ways that you can say it, but here's the symbol that means form. How do I put things together? What are the reactants and what are the products? Well, if I form ammonia, then this is a product. If I form ammonia from hydrogen and nitrogen, these are the reactants. Yeah. But is it this? Is it this? Is this the formula for ammonia? Well, the formula for ammonia is NH3, but the formula for hydrogen and nitrogen is not H and N. What is the formula for hydrogen and nitrogen? Yeah, it's H2 and N2. Remember, if I want this, then I'll say hydrogen atom. If I want this, I'll say nitrogen atom. Because in our nomenclature now, the words hydrogen and nitrogen refer to their natural formulas and states. Now, I didn't include the states in this reaction. We'll add those back later. But when I say hydrogen and nitrogen, I need to use my natural formulas. Okay, let's do this one equation. Let's balance this, and we'll just wrap it up there for the day. And so it might be helpful for students to write down the atoms, hydrogen and nitrogen, hydrogen and nitrogen. And it might be helpful to write down how many we have. And so the goal of balancing is getting these two lists of atoms to equal the same thing by adding stoichiometric coefficients. But remember, if I add a stoichiometric coefficient, the stoichiometric coefficient is telling me how many of the molecules or species that I have. So that means that I would have A times the number of N and A times 3 hydrogens. So I would have A times 1 for nitrogen and A times 3 for hydrogen. If I don't have a stoichiometric coefficient out in front, it's understood to be 1. That's why it's 1 times 1 for nitrogen and 1 times 3 for hydrogen. Okay, well, let's try to figure out how to get them to equal the same. Well, how could I do that? I think that I would start here with nitrogen. One good piece of advice is that you don't do hydrogen first. You do non-hydrogen, non-oxygen atoms first. And we'll spell all this out next time. But I've got 1 nitrogen on the product side and 2 nitrogens on the reactant side. So what could I put here in order to make the numbers the same? Yeah, 2. So how does that change the count? I have 2 nitrogens, but what do I have with hydrogen now? Now I have 6. Okay, so far I'm okay with nitrogen. Nitrogen is okay. I got the same values, but I still have to deal with hydrogen. So what can I do to get the hydrogens to be the same? Do I need to change anything for nitrogen right there? Do I need to add anything there? I don't need to add anything there, but what do I do here? I think you guys made some suggestions for me. If I do 3. If I change that, then it changes hydrogen from 2 to 6. And now my lists are the same, and so my reaction is balanced. Okay, so what I'm going to do is come back next time. We're going to write down they're not rules for balancing reactions. The only rule for balancing reactions is you have the same atoms on the product side as the reactant side, and they're in the same quantity. That's the only rule, right? The rest of the things we're going to write down will be suggestions. They'll be helpful hints for how to balance equations. But at the end of the day, the only thing you have to do is make the numbers and types of atoms on the reactant side the same as the number and types of reactants on the product side. They just have to be the same. Now, there is some hints and tips and helpful suggestions in order to make that a little easier for you. And that's where we'll start. We'll start there, and then we'll just do a bunch of practice. We'll just do a bunch of balancing chemical reactions. Then we'll move on to solubility. We'll talk about ionic equations and net ionic equations, and we'll put a lot of those pieces together, get a little bit more complicated with them. But at the end of the day, we're essentially into chapter 7, and I'm going to come into chapters, do some more chapter 7 on Monday, and we'll add a little bit more to it.